Hello! In this video, we are going to continue identifying and classifying isomers. So in the last video, we went over number 1 and number 2. In this video, we're going to go over number 3 and number 4. So remember, we're going to draw all of the isomers for each of those compounds. Then we're going to determine which of the isomers are chiral or achiral. If an isomer has a stereocenter, we're going to designate it as R or S. And then we're going to determine the relationship between pairs of isomers. All right, so again, we're going to focus on number 3, 2-bromo-3-chlorobutane, and then number 4, 2,3-dibromobutane. Okay, so for this one, let's just start by drawing the structure, and we won't worry about wedges or dashes or anything like that. We'll just draw everything in the plane of the paper. Okay, so the last part of the name, butane, tells me I have how many carbons? 4. So I'll just draw my 4-carbon chain. And then I'm told that bromine is on carbon 2 and chlorine is on carbon 3. So carbon 2, I'll draw a bromine. Carbon 3, I'll draw a chlorine. Okay. So now we need to draw all of the isomers of this molecule. But we can't really do anything different here than how we've drawn it because we were given the name of the molecule. So instead, let's kind of jump down our to-do list and let's find any stereocenters. So can you find any stereocenters? And remember, a stereocenter is an atom that's bonded to 4 different atoms or 4 different groups or some combination. So I see 2 stereocenters. The first one is carbon 2. The second one is carbon 3. So each of those carbons are bonded to 4 different groups. So for instance, carbon 2 is bonded to a bromine, a methyl group, the entire group to the right, and a hydrogen. But the hydrogen isn't shown because this is a bond line structure. And carbon 3 is similar. It's bonded to a chlorine, a methyl carbon, the whole entire group to the left, and a hydrogen. All right, so now we need to draw all of the stereoisomers for this molecule because we do have stereocenters. So is this molecule chiral or achiral, do you think? Well, since it has 2 stereocenters, I would assume it is chiral. Now, one reason why it might not be chiral is if it's a meso compound, so it has a plane of symmetry. This one doesn't have a plane of symmetry because we have a bromine and a chlorine, and they're different, so this would be a chiral molecule. Okay, so let's draw all of the different molecules here. So remember, if you have a stereocenter, you have 2 bonds that are in the plane of the paper, and then one that's in a wedge position and one that's in a dashed position. So let's just draw bromine in a wedge position and chlorine in a wedge position. We'll just do that to start. What are some other ways we could draw this? Well, we could draw bromine and chlorine in dashed positions too, right? So let's draw that. What are some other options? Well, what if bromine was in a wedge, but chlorine was in a dash? That's another option. And last but not least, what if bromine was in a dash, but chlorine was in a wedge? So these are all possibilities for this molecule because we weren't told specifically if something was R or S or if something was a wedge or a dash. We were just given 2-bromo-3-chlorobutane. So all of these molecules we drew on the bottom are possible. Okay, so in order to determine the relationships between each of these different isomers, we need to assign R and S to each stereocenter. Now, before we do that, I just want to give you a little tip here. The number of stereoisomers that a molecule can have is equal to 2 to the n, where n is equal to the number of stereocenters. So here we had 2 stereocenters. So we would write 2 to the second, which is equal to 4 stereoisomers. And in fact, we just drew 4 stereoisomers, so that's perfect. Okay, so let's assign R and S to each stereocenter. I'm going to start with the molecule on the left because once I know those assignments, I can actually figure out all of the other molecules' assignments. So you'll see what I mean in a second. All right, so let's start with carbon 2, our first stereocenter. So we're going to assign R or S, which means we need to prioritize all of the groups surrounding that carbon. And we're going to prioritize them from largest mass to smallest mass. So what would come first, bromine, carbon, or hydrogen? Bromine. Bromine is the heaviest. Then what comes after that? Would the carbon in this methyl group come next? Or this carbon attached to chlorine? The carbon attached to chlorine, because that, remember if you have 2 of the same atom, so we have 2 carbons, then you want to go down the chain and see what those carbons are attached to. And then it becomes a competition of which atom is attached to the heaviest atoms. So that carbon would have priority 2 because it's attached to heavier atoms. The other carbon gets priority 3. And then there's a hydrogen in the back that gets priority 4. But we're not going to draw it for now. We'll just leave it behind the plane of the paper. All right, so if we draw a circle from 1 to 2 to 3, it would look like this. So is that circle going clockwise to the right or counterclockwise to the left? It's going clockwise to the right. So would that be R or S? R. All right, so carbon 2 has an R configuration when bromine is in the wedge position. So I can actually go through and assign all of the other carbon 2s in the other molecules. So for instance, in our third molecule, that would also have an R configuration because bromine's in a wedge. Now, if bromine's in a dash, that tells me that we have an S configuration, so it would be the opposite. So we can also assign those stereocenters. Great, so now we just have to figure out if chlorine is in a wedge position, what is the configuration of the carbon that it's attached to, so the other stereocenter. And I'll use red for this. So for our other stereocenter, let's prioritize what that carbon is bonded to. So what would come first, chlorine, carbon, or hydrogen? Chlorine, it's the heaviest atom. So now we have a competition between two carbons. So a carbon that's bonded to 3 hydrogens, and then a carbon that's bonded to bromine, another carbon, and a hydrogen. So which one would win? The carbon on the left or the carbon on the right? The carbon on the left, because it's bonded to heavier atoms. And again, the hydrogen that's not shown is behind the plane of the paper, and that has lowest priority, so we'll just ignore it for now. Okay, so if we draw a circle from 1 to 2 to 3, is that going in a clockwise direction to the right or a counterclockwise direction to the left? A clockwise direction. So is that R or S? R. Okay, so the second stereocenter is also in an R configuration if chlorine is in a wedge position. So I can go through and assign R to the stereocenters that have a chlorine in a wedge position. And then the stereocenters that have a chlorine in a dash position will be the opposite. So I'll assign S to those. Okay, so our first molecule has RR, our second molecule has SS, our third molecule has RS, and our fourth molecule has SR. Now, before we decide how each of these isomers are related to each other, I just want to give you a tip on that as well. So I'll write that up above. So tip. If the stereocenters are all flipped, so when we're comparing two molecules, if all of the stereocenters are different, then the molecules are enantiomers. Now, if some of the stereocenters are flipped, but not all of them, then the molecules are diastereomers. Okay, so to make this a little bit easier, let's label these molecules A, B, C, and D. So let's look at A and B. What is the relationship between A and B? Are they enantiomers or diastereomers? So A is RR, and then B is SS. So when we're comparing the two, all of the stereocenters are different. So that means that they are enantiomers. Okay, so now let's compare B to C. Are those two molecules enantiomers or diastereomers? So molecule B has an SS configuration. Molecule C has an RS configuration. So only one of the stereocenters is different, not all of them. So that means that B and C are diastereomers. Okay, now let's compare C and D. Are those enantiomers or diastereomers? Enantiomers, because we have RS and then SR. So all of the stereocenters have different assignments. So the carbon attached to bromine goes from R to S, and then the carbon attached to chlorine goes from S to R if we're comparing C and D. So those are enantiomers. And then you could even compare A to C and A to D, etc. But that's probably good enough for now. So hopefully this helps with understanding the difference between enantiomers and diastereomers. Now let's go on to our last molecule, 2,3-dibromobutane. So I would like you to try to draw all of the isomers of 2,3-dibromobutane. And this will be pretty similar to the last problem. So feel free to pause the video, and when you're done, we'll go over it together. All right, so let's go over this one together. So similar to the last molecule, it looks like we have 4 carbons. Carbon 2 has a bromine attached, and carbon 3 has a bromine attached. All right, so where are the stereocenters? Carbon 2 and carbon 3. So this is looking very similar to our last problem, except we have 2 bromines here. Okay, so now let's draw all of our possible isomers, and to start, let's figure out how many isomers we have. So remember that trick, 2 to the n, where n is the number of stereocenters. So this would be 2 to the second, which gives us 4 stereoisomers. Okay, so that's just one way that we can check we have all of the possible isomers. So on the first structure, I'm just going to draw both bromines in a wedge position. In the second structure, I'm going to draw them both in a dashed position. In the third structure, one will be in a wedge, one will be in a dash. And in the fourth structure, it's the opposite. So the first bromine will be in a dash, the second bromine will be in a wedge. Okay, so now the next step, we need to assign R or S to our stereocenters. So let's start with our first stereocenter. And let's prioritize all of the atoms bonded to that stereocenter. So what would come first, bromine, carbon, or hydrogen? Bromine. And then we have a competition between two carbons. So which one would have greater priority, the carbon on the left or the carbon on the right? So the carbon on the right is bonded to heavier atoms, such as bromine, so that will have greater priority. All right, so we'll just leave our hydrogen alone. It's our lowest priority atom, and it's behind the plane of the paper, so that's fine. Now let's draw a circle from 1 to 2 to 3. Is that going in a clockwise direction to the right or a counterclockwise direction to the left? Clockwise. So is that R or S? R. All right, now let's do the same thing for the second stereocenter. So which atom has highest priority, bromine, carbon, or hydrogen? Very similar to before, bromine does. And then we're competing between two carbons. So which carbon would have second priority, the one on the left or the one on the right? Well, the carbon on the left is bonded to a bromine and another carbon, which are heavier than the hydrogens that the carbon on the right is bonded to. So that will get second priority. And then hydrogen again is in the back and has lowest priority, so that's fine. So now let's draw a circle from 1 to 2 to 3. So is that turning towards the right in a clockwise manner or towards the left in a counterclockwise manner? Towards the right. So is that R or S? R. All right, so this is looking very similar to our last problem, right? We have two R's for the first molecule. And then let's go through and assign the stereocenters in our other three molecules. So for carbon 2, we said that we have an R configuration if bromine is in a wedge. So that must mean that when it's in a dashed position, it's S. And then for carbon 3, if bromine's in a wedge position, that's an R. If it's in a dashed position, that's an S. All right. So let's figure out the relationships between each of these stereoisomers. So let's label these A, B, C, and D. Okay, so what is the relationship between A and B? So we have RR, and then in the second molecule we have SS. So all of the stereocenters are different. So that means that these are enantiomers. What about B and C? Are they enantiomers, diastereomers? So we have SS for molecule B, and then RS for molecule C. So only one of the stereocenters is different when we're comparing the two molecules. So that means these are diastereomers. And then what about C and D? What's the relationship between those? So we have RS for C and SR for D. So initially, we might assume that these are enantiomers, right? All of the stereocenters are different. However, what if we flip structure D? So let's just turn it over 180 degrees. We end up with the same exact molecule as C. So notice that we took this bromine and just kind of rotated it up. This bromine we just rotated down. So we really were just turning the molecule 180 degrees. And that just gave us molecule C. So C and D are actually identical to each other. So that was kind of a trick question. Now, one way you can also test for this is looking for a plane of symmetry. So what would happen if we rotated our first molecule A, but let's say we just rotate one of the bromines up. So let's say we rotate it like this. Oh, and let me make a little bit of room here. So the bromine on the bottom facing down is in a wedge position, but if we flip it up so that it mirrors the first bromine, then it will be in a dashed position. And I recommend building a model of this molecule from your modeling kit. And then you can kind of see when you rotate the bromine upwards, it ends up in the back or towards the back of the molecule. So this first molecule does not have a plane of symmetry. So that is a chiral molecule. Now let's check molecule B. Let's see what that would look like. So the first bromine stays the same. We're just going to rotate the second bromine up. So initially it's in a dashed position, but if we rotate it upwards, it will be in a wedge position. So again, we don't have a plane of symmetry there, so that is also chiral. Now let's look at molecule C. So molecule C, we'll leave the first bromine alone, so that's still in a wedge position. But if we rotate the second bromine up, it will go from a dashed position to a wedge position. So now there's a plane of symmetry there. So this is actually a meso compound. And then we already said that molecule D is identical to molecule C, so it also has a plane of symmetry, and it's also a meso compound. Or, you know, we could say it's just identical to molecule C. So meso compounds are achiral. So even though they have stereocenters, because there's a plane of symmetry, they are achiral. So again, if we were to draw a mirror image of molecule C, it would be superimposable on the original molecule. So again, it is achiral. So we can also write for molecule D that that is achiral because it's exactly the same as C, right? Okay, so we kind of covered a lot in the last two practice problems. We figured out how to identify enantiomers and diastereomers, but we also saw that you have to check sometimes to see if you have a meso compound or identical compounds. So it's always good to also check if you have a plane of symmetry. All right, so in the next lecture, we're going to go over cis and trans isomers, and we'll talk about what those look like, how to draw them, how to name them, etc. So I will see you then.